I'm going to talk about the same paper, about Sumcheck over fields of small characteristics, because the previous time I only managed to cover Sumcheck and I didn't go into the algorithm. So yeah, I'm going to, oh, that's my pen, so, okay. So while I'm writing this, I'm gonna sort of talk about what I'm gonna cover. Okay, this is better. Yeah, so I'm gonna briefly cover the motivation again, and then sort of cover. So there's gonna be 3 algorithms presented in the paper, but I'm only gonna talk about 2 of them, which is algorithms 1 and 2. 1 and 3, sorry. I'm not gonna cover algorithm 2. But the key point is that sort of, like I mentioned the previous time, because in algorithm 3, you're sort of doing more base field operations over doing less extension field operations. And that's sort of the saving you get from using a different algorithm. And then midway, what they found in the paper was that you can switch over from algorithm 3 to 1 at some point in the protocol to save on prover costs, basically. So I'm going to start off with a bit of motivation. So why are we looking at small fields, right? It's sort of because recently there's been a lot of advancements in small fields, right? And you have the idea that once you have small fields, you have better performance because if you have a 32-bit field, then it works very nicely for hardware instead of working over 256, and then you have to sort of work with limbs and do all sorts of checks on the limbs as well. And also, of course, we have like the recent work on Venus, where they found like faster commitments for small values, and that could mean that we end up having Sumcheck be the bottleneck, let's say. And so some observations, right? So I'm going to write down some observations of the current state of Sumcheck, I guess, that they found in the paper. So about, let's say, like half of the operations are actually in extension field. I guess half are extension field operations. And roughly speaking about the costs, a degree for extension field operations is about, let's say, like 9 to 16 times more expensive than a base field operation. And in Venus, at least, what they make use most of is degree 8s and degree 128s, I believe, because they're working over the GF2. And to get enough security, you kind of want to work over, let's say, a degree of 128s. In some cases, when you work over these fields, you sort of get operations for free, because like 0 multiplied by the extension field is you get 0, and then by itself you get the extension field. So those are just some basic observations, and I'll go into the actual algorithms now. So I guess even before I go into the algorithms, I want to write a key lemma here, which is lemma 1 in the paper, which states that you're going to have this relationship over here. Oh, not relationship, but you can restate a L-variate multilinear polynomial as something like this. So if you have something like this, you can actually re-express this as something like this. And so, okay, maybe I should actually write this here because I want to use most of the board. So let me write this here again. So lemma 1 x prime plus 1 minus 1. And while I'm here again, I'll write some costs notation that they use in the paper. So again, they use these terms BB, BE, and EE. BB meaning base multiplied by a base field. And BE, you have base multiplied by an extension field, and finally extension field multiplied by extension field. So they use this to sort of denote their costs in the paper. Okay, so I'll jump into the actual algorithms now. So I guess the problem that we want to solve in the paper is the sum of, say, two polynomials. So we want to solve for this we want to solve for px multiplied by qx over, and we want to sum over this multiplication, let's say, over the interpolating sets of L. And so the algorithms presented will in the paper, they talk about rounds 1, 2, and then the ith round, let's say. So I'll talk about a bit about those rounds. So in algo 1, what they do is they store the evaluations of P and Q in separate arrays. So let's say they have like array A and array B, and they're storing the evaluations here. So let's say you have like index I here, and this would basically be, so A of I will contain evaluations of, so this would be polynomial P and Q. So this would be evaluations over P of I, and let's say like this would be Qi, let's say. So and then in round 1, what they do is they have this expression that you want to check, which is, if you recall in Sumcheck that we want to do something like this check. That you want to calculate S10, S11, and then because this is going to be at least degree 2, right? Sort of. So you're going to do S11 as well and S12. So if we remember the actual problem that we want to solve, we want to solve for this, right? We want to solve over the sum of P 0 and Q 0 of x, right? But because we are storing the evaluations here, what we can do is actually just index into the arrays that we have here. So then it would be something like, I won't write this, so it would just be something like this. And then we do the same for S1 of x. And I'll spare the writing because it's the exact same thing, except that you change the 0 with ones. But S12 is slightly different, and that's where we'll use lemma 2 actually. So S12, we will want to calculate this expression. Which, if we look at lemma 1 again, we can sort of re-express this as something like, so it's fairly long. Maybe this is a bit hard to see, so I will write here. So you get something like so this is just simply using lemma 1 to re-express this problem as something like this, which we can calculate from previous values. And the final part of this algorithm is that the verifier basically selects R1 and then updates this array. So how this update takes place is that's for, let's say, for AX. And again, I'm only going to do this for one array because it's the same thing for the other. So you're selecting the challenge point R1, using the previous value, A0 of X, and then adding R1 and A1X. You're updating it into AX. So you do this again for the entire array. So, right, so we have round 1. I'll jump now into round 2, and let's write here actually. I'm going to use this space. Okay, so in round 2 again, we're going to do something very similar. We're going to calculate S20, S21, and S22. But this time we can just reuse what we have from before. So again, this is going to be just A0X. Remember, we pre-calculated this in the previous round, installed in the array. And then S21 is using this expression. And for S22, again, we're going to have to write this out, but I'm going to write this out for a reason later on to compare with algorithm 3, so bear with me. So we're going to have this, the thing here to take note is that, remember here we have the R. So we'll come back to this later, but this would be important later on. So this would turn out to be something like, say, yeah, 1 minus 2, p or 1 plus and multiplied by 1 minus 2 q 0x plus 2 q x. Okay. And I also write the brief costs of this. So this is how you would calculate for the second round. And basically for the ith round, it's sort of the same thing. And the rough cost for this is that if you have Si of 0, Si of 1, and Si of 2, the cost is going to be sort of like n over 2 I minus 1 extension multiplications. And updating also costs the same. So the updating of the array that I showed earlier, both of them have the same costs. So both of them end up costing about that amount of extension multiplications. Okay, so that's it for this algorithm, the base algorithm that we have. Now we're going to move on to the optimized algorithm. And I'm going to leave S2 of 2 here to show something later on. And also the cost profile as well. So in algorithm 2, or 3 rather, in the paper, the sort of the key observation here is that whenever you have something like P R1 of X, these are basically extension field elements, right? Because of the challenge point, because you're getting the randomness here. But they are actually just re-expressions of base field elements. So you can actually express them as a linear combination of base field elements. And I'll show this by showing how you calculate round 1 in S1 of 2 later on. But in algo 3, instead of having 2 arrays, what you have is just 1 array, which is C, and you store actually evaluations of Px times Qx. And then let's say Cx would be basically the evaluation of Px Qx, let's see, like here. Or maybe I would be more appropriate, I guess. And just keep in mind, because you're doing this up front, you're already doing base field multiplications here. Which is, I mean, depending on the size, it would be like n base multiplications. And again, for those who just arrived, remember we have the notation here, BB meaning base times base multiplications. So in round 1 of this algorithm, when you calculate S1 and S1 of 1, S1 of 0 and S1 of 1, recall that we want this P0 of x and Q0x. But because we already computed this, we can actually just index into the array. So all we're doing is a sum of Cx array. So using what we've already pre-computed. And same for S1 of 1. So I'm not going to write this out. So the trick here is that when we are calculating S1 of 2, and I'll write this out because it's important, what you're doing is actually this. So you have P 0x multiplied by q 0x plus for p 1 of x multiplied by q 1 of x. Oh, sorry, this is not a dot, this is a comma. Subtracted to q 0x and multiplied by p 1 of x. And I promise this is going to be the last one I'm writing. P 1 of x is 2p 1 of x key. Right. I'm done. Okay, almost done. 2 more minutes. So the key observation here is that we are sort of doing the same thing here, right? But here you're using the R's, which is extension field elements, right? But here, if you re-express this as such, what you've noticed is that this you've already pre-computed, right? Because we had this before. So these are quote-unquote free in a sense, because you've already done this here when you're storing it here. And all you have to do is just more base field multiplications, cross terms basically. And with S2 of 2, you do a similar thing. But the cost profile kind of blows up because you can imagine as you go deeper and deeper with more random challenges from the verifier, you have more base field multiplications. And to finish up, I'll just briefly, again, write down the cost profile, which I wrote before, but this time in the clearer manner. Yeah. So I said before you're using mostly just the GF2 base field, right? And when you have a degree 4 extension, what they found was that there wasn't actually much of a difference. And the key trick of this is that you end up switching from what I described here back to the first algorithm at some point in the protocol. So they found through their experiments where they should switch the algorithm. So I'm just going to write a few data points here. They have a more extensive research in their paper, so I suggest reading that if you're interested. But I'm just going to write the ones that we are keen on, which is a degree 4, 8, and 128. And the key thing to take note here is that at degree 4, there actually isn't much improvement. So it's about like a 1.3x faster. But what you see at 128 is you see like a 10x faster improvements of the algorithm. And then they found that's where you should switch from algorithm 3 to 1 is at this point in particular. So for degree 1 to 8, you would switch at round 7. So what you do is you do this for 7 rounds and then switch back to algo 1 for the rest of the protocol. And yeah, I think that's it for my talk.